You
First
look
of all,
marvelous.
this is my great pleasure and meeting you all at this event, Optical Sciences Winter School, OSWS 2022. As you can see, we have 58 people joining this session at this moment live. I am so happy we are all here together this morning, starting 2022 together. And before we begin the official session, I want to share a video very briefly. So please pay attention here. And this video shows you what happened in order to prepare all the boxes delivered to your home in order to make this winter school hands-on, something we can do together, although it's a virtual event. And I want to make sure this is all prepared by our student organizing committee at our college. You'll meet them throughout the 3 days to come. I want to make sure this is really for students, our future. This is not for us, faculties, or some leading organizations, thankfully supporting this event like Optica, SPIE. We have foundations. You will all hear their names later, this event. But this is truly for students, you all attending here. And it is also prepared by this thankful students committee effort, as you saw in that time-lapse video. I wish we all enjoy and appreciate each other, and we can truly make this event centered around our future students throughout the 3 days, so that we can inspire all of you. And at the end, we wish you love optics. That is the maybe only motivation why we are doing this. With that, without further ado, I will introduce our dean, beloved dean, Tom Koch, eagerly waiting for his turn, and he will give a great opening remark and presentation, introducing what this is all about beyond what I just said. So with that, Tom, would you please lead us from here?
Very good. Thank you,
Thank
Daru. Is my audio working okay?
Yes, very well.
Very good. Well, I'll hope that my screen sharing works as well. Let me share that. Can you all see that reasonably well?
Yes, very well.
Okay, very good. Well, welcome everyone. And it's a pleasure to have you all here. This is actually a splash screen from our college. We have a video that we show about optics there, and it has our catchphrase about lighting the future. We've also, of course, it needs to be updated. We are now the Wyant College of Optical Sciences, and I'll give you a little inclination or a little glimpse as to why that name change took place. But fundamentally, here to welcome you, and it's a pleasure to see you all. And we wish you could be with us here in sunny Tucson. Right now, today will be in the mid-70s. So for those of you who are chilling out, literally somewhere on the East Coast, perhaps, or somewhere colder, wish you could be here in sunny Tucson. So the team that puts this together has come up with this way cool new little logo, and we're now many years into offering this winter school. It was called the Winter School and Workshop because it was maybe a more complex program in some of the earlier years. At this point, we're just calling it the Winter School, and the objective is, as Daewoo said, it's really all about you. It's trying to pick out some very promising undergraduate students across the nation or even internationally now, and expose them to more of optics and photonics than they may be aware of today. I heard some of the discussion. So many of you are already deep in this, but some of you may not appreciate some of the breadth and scope of what goes on in this field. And so we'd like to encourage you to be aware and then be motivated to pursue what we believe will be really rewarding careers. And we found that ourselves, that we really enjoy what we do, and it's very rewarding both as a profession and just a stimulating career. So here's a picture from 2020, and this was actually the last in-person event. So if you were here in person, we would gather together at our building, and we would be convening in our auditorium. But thanks to COVID, last year we went online and actually found that it was quite successful. So there, even to the extent of having lab visits and things like that. So you'll see that in the program over the next couple of days. And we hope that you will also agree that it's successful when it's executed in an online fashion. I updated this map myself. It's probably not accurately done, but you can see that we've got a really broad representation of universities from across the whole country, and even now extending internationally. We have participation from Germany and India with this event, with speakers and students. So maybe in the future this will even expand internationally. We'll have to see how it goes. Here's a list of at least I think it's the most updated list of who's here. So you all just introduced yourselves, but there's 39 participating schools. And then, as Dawook said, there's 6 societies, foundations, and companies that are also participating. And at last count, we had 56 student participants, in addition to some of the others right here on campus who've helped support this. So it's a really broad cross-section of universities, and many of these are highly research active universities with very in-depth graduate programs, but others are not. And especially to those universities where there's not a really kind of high profile graduate program in optics, this is a great opportunity for you to see maybe a little more scope about things that are going on in the field than you could learn at your own institution. As Dawook also said, we are really happy to have sponsors that support this financially. In normal years, that includes airfare, where we would fly you out here to Tucson and cover your airfare and your lodging and your meals and so forth. During the COVID, some of those expenses have been reduced, but we've also done things like make the kits. And Dawook, I didn't get one of those boxes. I want one of those. They look pretty cool. So I think I need one too. So we'd like to thank the organizing committee as well. This is a group of 9 of our faculty, and Catherine Schumann, who's I think I left out an N, Catherine, I'm sorry, who's our events coordinator, and also the student organizing committee, whom you will meet throughout this event. And they've been really, really helpful as well. So if you're here in Tucson, I usually start out welcoming you to Tucson. And it's a really cool place, or in the winter, it's actually a nice warm place relative to where you may be. And, it's kind of like Dorothy and the Wizard of Oz. When you're here, we say, you're not in Kansas anymore. It's a really different place. Lots of flora and fauna that you don't see in other parts of the country. And it's actually not that hard to see all these things. So all these pictures of animals I took myself, and what's more interesting is they're taken from the same spot inside my bedroom, just looking out a window on the side of my house. So lots of wild animals to see that you won't see in other parts of the country. A lot of hiking, a lot of outdoor activities with the mountains. Very fun place. And I'm also going to take a moment just to introduce you to the University of Arizona. Throughout this workshop, you'll hear presentations from our sister optics institutions across the country, a number of those who are close partners with us. But this is a chance to kind of toot the horn of the University of Arizona. So we're a large state school, colleges spanning all kinds of disciplines, but we are one of the unique universities with an optics college, a whole college dedicated to optics and photonics. And the university overall is very research intensive, with pushing $800 million of research activity, funded research activity every year. And we're usually ranked in the top 3 or 4 in physical sciences. And part of the reason for that is we have a large footprint in space science with a lot of large NASA programs. And those are counted in the physical sciences category. An example of that, I say down here, we do big science. One example of that is we are the prime on a NASA mission that's underway right now to land on an asteroid and collect a sample and bring it back to Earth. And that's a fun project. Lots of people at the university got engaged in that. The samples, when they come back, some of them will come right here to the university. And some of the camera systems that were used on that mission were actually made by our college. And so this picture shows the campus, and then out on the mall there, you see the College of Optical Sciences, which today is 3 buildings connected together, and as a group, they're called the Meinel Building. So as it says here, very sunny, nice weather, blue skies, wish you could be here. By the numbers, we are the largest optics undergraduate and graduate education and research program in the US. We've got about 37, 38 tenure track faculty, plus about 25 or 30 research faculty. And we have joint appointments in all kinds of disciplines. So lots of people get engaged in our optics programs from biology, life sciences, physics, electrical and computer engineering, and so forth, to do collaborations. And sometimes that's because they want access to our students. We get very, very good students, and they'd like to get them involved in their graduate programs as well. We started out mostly as a graduate program, but 50 years ago, 57 years ago, I guess. We still are predominantly graduates, with about 170 PhD students here at any given moment, and about 130 master students. But we also have an undergraduate program, sophomores through seniors. The freshmen come in, we don't recruit directly out of high school, so they come into engineering or physics or another area, and then we lure them into the optics college, because frankly, they don't know what optics is when you're in high school. And that's going to be one of my themes in the slides that come. Now, I mentioned that we are now the Wyand College of Optical Sciences. We got a huge injection in our endowment, both to support graduate students, PhD students. So all of our PhD students are now covered in their first year without needing to commit to a specific graduate thesis advisor and project. And that's, again, because you don't really know. The majority of our students come in and they think, even when they think they know what they're going to do, they go, oh, wow, I didn't know you could even do that. And I'm going to switch. So most people end up switching around and when they learn about the scope of things. But we also now have 14 new endowed faculty positions, and that's going to amount to about a 35% growth in the size of the college over the next 5 years. So it's an exciting time here in Tucson. We will be growing in all these areas: quantum networking and biomedical optics, imaging, for the future autonomous system and human intelligent interactions with the cloud and various technology. All of those technologies are optics mediated. And we've always been big in space-based imaging and advanced materials and optomechanics. So growing on all these fronts, and new advances in our curriculum, and a new building, and actually that's under construction. I took this about 20 minutes ago out the window. I walked over to the window and snapped it from the 7th floor. So this new building will be a $100 million 7-story building, and we will be the dominant occupant of that to make us 4 buildings rather than just the 3 we have now. So let's go back to this. Why are we having this winter school? And frankly, I mentioned, when you tell people, I sit on an airplane and people say, well, what do you do? I say, well, I'm in optics. And they go, oh, yeah, optometry, yeah. do you guys actually, do you have one of those little screws for the hinge? Because my glasses need that. And so, yes, we have people who are involved in ophthalmology, and we, in fact, some very exciting work in that field, but optics is so much more than that. And we think a really good example of that is the things that are really ubiquitous in your life today. If you look at your smartphone, you know, you almost can't survive today without a smartphone or a tablet with you at all times. And if you look at that, the display is some pretty amazing high resolution color, usually now organic LED displays. And if you crack that thing open, the ultra precision case is made with laser molded, laser machine molds and things like that. And we used to laugh, you know, you guys wouldn't know this, but when they first came out with these cameras and cell phones, we thought it was kind of goofy because there could never be a decent, at least we thought, couldn't be a decent camera. And now the cameras and cell phones are just astounding. And not only one camera is shown here, but you may have half a dozen cameras in your cell phone on the front and back, doing all kinds of things, not just for photographs, but they're there for 3D telemetry and imaging and sensing and so forth. So these very small, ultra precise components and the focal plane arrays that go into those camera systems. And now, as I mentioned, on the front, it's just smattered with photonics. There's projectors, dot projectors, and and cameras and LiDAR systems, things like that. So very, very sophisticated stuff. And you know, when this is a funny, you know, James Bond movie way back in the day, lasers used to be big scary things, and now the lasers of today. Actually, it was one of our students, Jack Jewell, who's now supporting scholarships and endowed chairs here in the college, was the inventor of the vertical cavity surface emitting laser. And in a period of months, when the iPhone 10 came out, there were more lasers shipped in a few months than in the entire history of the laser before that, of all kinds of lasers, anywhere, anyhow. And it's because this is now 300 lasers ship in every single iPhone, and it's just going crazy. So this kind of technology is pervasive in our lives. And, you know, people don't really appreciate that this is what optics is. And then if you go even deeper and you look at why this iPhone or why your smartphone is, you've got a chip in there with 12 billion transistors on it. And that's increasing every year, more and more and more. These things are just shrinking to be so small. And you could never do that without the amazing lithography systems that they have now. So these are EUV extreme ultraviolet printers that use really crazy laser pellet, deep UV light that's from carbon dioxide laser illumination of these pellets as they fly through space, and all done in a vacuum. So to be able to stay on Moore's law and continue with that, it's all optics as well. And then once you connect up, yes, you connect up with Wi-Fi or LTE or 5G, but once you get into the internet, that's all optical communication technology. And a single fiber can now carry upwards of more than 1 petabit per second. And you can't really fathom what that is, but if a good example is if you took every household in the US and had them downloading at 10 or 20 megabits per second, you could do that on one hair thin optical fiber. That's how much information you can fit on one fiber. So it's amazing technology. And then when you look at what the internet is, everybody thinks about these long fibers, but it's actually these data centers. So when you connect up to the internet and you look inside that data center, it looks like this. It's just row after row after row of servers. And guess what? They're all connected together with massive cabling of optical fibers and laser transceivers that connect all that up. So maybe upwards of 1 million lasers inside one of these modern data centers. So that's a better example of what optics and photonics is, at least in our mind. And over the next couple of days, we're going to expose you to research in fields like that. That was just one example. There's all kinds of things in biomedical and in quantum technologies and fundamental physics. So, what is research? Well, my own view is research is when you're trying to do something where you really don't have a clue what you're doing. You're brave enough to try to do something when you don't know if it's going to work. You're not sure if your approach is right. That's what research is. And there's a huge amount of serendipity and discovery in that, both in, even if you prove the premise that you set out to do, quite often you stumble and realize it didn't work the way you thought it was going to work. And that's when you have real discovery. And so a lot of it comes from mistakes and errors and strange things that you observe along the way. And to those who are observant, they may win Nobel Prizes. And those who get annoyed by this quirky phenomena and push it out of the way miss their Nobel Prize. So you want to be open-minded. And these are some of the folks from 2018 Nobel Prize, and we all in our field know them all pretty well, quite often very personally. And if you look at the history of Nobel Prizes, 92 of them were really related to optics or optics-enabled advances. So this field is not only impactful from technology in our lives, but really, really at the core of fundamental science and advances. So very, very exciting field to be in. If you look at how we divvy things up here at the College of Optical Sciences, we don't have departments. We have this big flat organization. And we kind of enjoy that because everybody gets involved in everybody else's work. But we do have 4 areas of discipline. One of them is optical physics, and you'll get a sense of some of the things that people are doing there. This is atom optics and quantum optics, quantum nanophotonic, extreme nonlinear optics. So light that is, when it propagates, it's so intense that in one single optical cycle, it rips apart the atoms, and then the electrons go flying out and then come slamming back in the second half of the optical cycle, 10 to the minus 15 seconds later. So crazy, crazy nonlinear optics. And how does light propagate when it's that intense? And then optical engineering, and this is related to all kinds of designs of things, including ophthalmology. And one of our faculty is Jim Schwigerling, is the inventor of a new trifocal contact lens that is now getting widely deployed around the world. So he's a patent holder of that, and it's rewarding him very well, as well as the college. But more fundamentally, it's having impact on people's lives. Real stuff improves your life, and that's true in whether it's smartphones or some of the stuff you'll hear about in our first faculty talk. With AR, VR technologies and things like that, but also the telescopes for astronomy and optical fabrication and so forth. Image science is related to kind of like image processing, but it's much more than that. It's how do you quantify the amount of information that's in an image, and then how do you design systems that are provably optimizing your ability to execute a task based on that image, based on that information? And the answer may be, well, it doesn't have to be a good image. It may be a crappy classical image, but it gives you that information better than anything else. And if you co-design your algorithms together with the hardware, you can get very, very high performance systems where you're minimizing cost or maximizing performance, minimizing size, weight, and power, and so forth. And then photonics, think about conversion between optical and electrical signals, optical communication technology, focal plane arrays, fiber optics, semiconductors, and a lot of our laser technology here in our college is in that group as well. So here's a snapshot of your agenda. I threw this together from the spreadsheet that you all have. I think I got it right. So I will sign off in a few minutes, but you've got talks from people spanning these different disciplines. Every year, this is a different list, so you won't hear everything. you'll hear a sampling. And we have speakers from around the world, including Martin Wegner from KIT over in Germany this morning. And then tomorrow, we'll hear more talks, and we have talks from our colleagues at University of Rochester, Montana State, University of New Mexico, North Carolina. So these are partner optics institutions from around the world. And we would really like you to think of this as not as a parochial Tucson event. It's really about our field. And we will be happy if you get excited and go to any one of these institutions, because we want to get people to support the amazing future that this field brings. And then here's the third day on Friday, again, with more presentations from faculty and students. So we also have students from talks from alumni who are out there in the field working in companies or in research institutions with panel sessions where you'll get to ask them questions like, what's it like? Do you like what you're doing? Is it fun? Are you glad you did it? Things like that. Now I get to cheat. And it's because my own field is photonics. So I always feel like they can't have enough photonics. It's like in Saturday Night Live, more cowbell. You need more photonics. So what is photonics? Well, I mentioned it. It's all these different disciplines, and there's very few fields, I think, where you pull together so many of the things you learn in physics and electrical and computer engineering and so forth. So you actually use your quantum mechanics, and maybe you even use your quantum field theory. You certainly use electromagnetics and semiconductor device physics and so forth, material science. So you get to synthesize all these things to make widgets. And what are the kind of widgets you make? Well, some of them are related to fiber optics technologies, maybe, and these are examples of femtosecond laser technology where you can do extreme nonlinear optics. And one of our faculty, Khan Q, actually found a way to miniaturize this and replace these $150,000 Ti sapphire lasers that everybody's got on their table with this little handheld thing that runs year after year. It's like the ever ready bunny. It just keeps running and running and running perfectly year after year. And it costs 10% of the price of one of those things. So handheld femtosecond fiber laser technologies. And then here's an example of the semiconductor laser. So this is one, not the vertical cavity laser. This is an edge emitting laser, and it's called a distributed feedback laser. And the reason I'm showing it is just to show you inside this chip that's only a couple hundred microns long. There's an amazing level of sophistication of epitaxially grown crystals that are etched and then regrown. And in this case, there's a grating that runs along the whole length longitudinally where the light propagates. So rather than using mirrors for feedback, this laser uses reflections off this grating continuously along a waveguide to make this laser resonate, but it works really well at one frequency. And that's why it's used in optical communication. And if you peel the onion and look inside that, there's all these layers of semiconductor. And if you look at the lattice for this thing, these aren't like just deposited layers. This is, even though it's all these different materials, it's one crystal lattice. All the atoms line up in one crystal in this whole thing. And if you look even more deeply in there, you can see the edge view of that grating down below. And then if you look at the waveguide, you can see deep in there that there's all these quantum wells that make the laser work better. So it's a quantum well laser. And then now today, people are putting these things together in photonic integrated circuits. So rather than having a zillion transistors on a chip, now they have a zillion lasers and optical waveguides. And these are now no longer fantasies. These are at the core and the heart of the at the internet. So the coherent communications that's taking place across the internet today, where your cell phone, the optical signals are really being manipulated the exact same way your cell phone signals are, with high levels of encoding and using quadrature amplitude modulation, 16 QAM, things like that. It wouldn't be possible without these photonic integrated circuits. So this stuff is now very real, and you're using it today, whether you know it or not. And I'm excited that we are part. I think Tom Brown is on the agenda later, later, I think tomorrow, or maybe today. And he'll be talking also about the University of Rochester's program, and they are a partner. The lead of this is in New York State, and it's SUNY Polytechnic, and it's a coordinated group, and we just got renewed for our next 7 years to make that kind of photonic integrated circuit technology accessible to you. So you can sit at your desktop and design photonic integrated circuits and get them made and delivered to conduct your own experiment or your own function. So this is how integrated circuits started out with Moses and foundries, and we're now doing the same thing with optics and photonics as well. So our university has been home to an engineering research center with NSF, and this shows the Center for Integrated Access Networks, where we led for the prior 10 years the only optical communication technology NSF center in the country. And now today, that ran its 10 years. Now today, we're just starting the newest ERC, where we're leading the Center for Quantum Networks. So this is, and our core partners in that are Harvard, MIT, and Yale, but other universities participate as well. And this is to try to connect quantum resources, whether they're sensors or quantum computers, in native quantum form. So rather than having optical fibers or wiring or cables that connect these things up, they're connected with extended quantum entanglement. So what that really means is remote states and these quantum computers or quantum sensors actually become coherently connected together to be a single quantum state across large distances, maybe across the country, maybe across the world. We're even in discussion with NASA about launching systems in space to do entangled quantum communication. So it's very cool stuff. My time's up. I want to thank you for coming. And we've got an exciting agenda. This is, again, looking at the first day. And our next talk is Hong Hua, who I saw joining us. And she's going to be talking to you about challenges and opportunities in AR and VR technology. And she's done an incredible amount of work in that field and has really good industry partnerships as well. So thank you all, and again, welcome. And I don't know if Daewoo, if you, I know you have a lead who's introducing each speaker, so I'll hand it off to whomever that is.
Thank you very much, Tom. It was a great opening talk, setting the tone, very nice. And I want to invite Lars, who is introducing Hong. So Lars, please.